Hello, my name is Abir Khan. Welcome to our presentation on our latest paper, debating whether more persuasive LLMs leads to more truthful answers. This was joint work by UCL Dark, Seri Match, Speechmatics, and Anthropic. So what is the landscape which motivates our research today? Fundamentally, it's a story of progress. This is a graph from contextual AI, which shows dates where benchmarks were introduced, and they're reported so to progress, normalized by human level performance, which is the black line. For example, you can see MNIST starting in 2000 here, and by 2014, we have human level performance. So we get to human level performance, that's great. But this is only half the graph, actually. Psych. What's really interesting when you look at like the last 5 or 10 years of progress is that it's really clear that we're getting to human level performance much quicker than we used to. And in particular, we also go beyond human level performance, as in we go beyond this black line way more than before. So the first factor to really take away is that we get and we go beyond human level performance much more than we used to with our systems. The second thing is that for alignment, we need high quality supervision. This is a schematic for what looks like regular training of like large language models today. You can see that we use like over 1 trillion tokens for unsupervised learning, which gets us our baseline capabilities, which is like the ability to do like reasoning, arithmetic, all of the tasks that we care about. And then what we have is a really high quality supervision data at the end, which is 4 orders of magnitude less data, which is used just to elicit the capabilities that we care about or make the model that's aligned and is doing the and can do the tasks that we care about. So the second thing to notice is supervision is super, super important here. In particular, we need high quality supervision. So what does that really mean? Well, it means that ML training in 2018 looked a bit like this. For example, on the x-axis, you have like alignment, which is how much the model does what you want it to. And on the y-axis, you have capabilities, which is like, what does the model know how to do? So we can think about training like a ResNet 50 from scratch, like tabula rasa, where it learns what a dog is by learning ImageNet or learning a classification task over ImageNet, and also becomes aligned to be a dog classifier because we train it on those labels. So we get both capabilities and alignment at the same time under like traditional ML training, tabula rasa 2018. But the world in 2030, I think, looks really different, right? If we keep doing large unsupervised learning and then we just do some like RLHF style fine tuning or supervision at the end to elicit the capabilities that we care about, what we end up having is really strong base models, which are really capable, have tons of reasoning and capabilities within them. But what we don't have is techniques that mean that we can align them with labels uh, in the same way. And like examples of this, where we already have weak supervision, is something like hallucinations in language models, where models just like regurgitate anything as opposed to just factual information, or where models are sycophantic instead of like giving us honest information, they give us information that would mean that they get a high RLHF score, or like regurgitate like the views of the annotators. Finally, models also have a propensity towards reward tampering. Uh, and like all of these things can be like attributed to having a weak supervision, like weak supervision. So what's really the problem here? The problem is here that there's no ground truth label anymore. There's no way to like tell something that's really smarter than you how you want it to act in a situation where you don't know the answer. What we like instead is a way to provide reliable supervision in the form of labels, reward signals, and critiques to models that remain effective past the point that models achieve broadly human level performance, or at the point at which they're better than the overseer, the thing that's meant to provide the supervisor label. We want to still be able to provide reliable supervision. This is probably like the desert data for like work in 2025, I think. This is the work, if this is like what we should be working towards. But the question is like, how do you operationalize it? And on the graph here, we have like a new setup or a sandwiching paradigm originally by Ajay Kotra, which suggests that the goal should be to develop methods that enable non-expert overseers to be as capable as expert level overseers. So you can imagine what we'd like to do is enable high school students to be able to supervise math answers or check math answers that a university level model has produced. And the way that we're going to do this setup to make sure that it makes sense is we're going to choose tasks where systems are more capable than most people, but we're going to have some, but not more capable than some expert out there that can still check the answer. And then we can still use that expert to check if our oversight mechanism makes sense right now. But also we're certain that it definitely enables humans to be better supervisors or overseers methods. So what are we actually going to do? Well, we're going to have this capability gap or expertise gap that we're going to talk about. And what we're going to use is we're going to use comprehension stories from the Gutenberg stories. They're about 8K in token length with 2 candidate answers. What we're going to do to make this for this task is we're going to make non-experts not have access to the text, and then we're going to ask them to answer comprehension questions, which is a seemingly impossible task. You can't answer a sci-fi comprehension question without having read the without reading the sci-fi text associated with it. What instead we're going to do is let LLMs have access to that text, and then we're going to try query those LLMs in a way that helps us know if the answer is correct, to help the non-expert find the correct answer. If you want to look at this in terms of like the previous picture of sandwiching, what we do is we have some experts that still have access to the textbook. But then what we're going to see is non-experts without the textbook can use an LLM to get the answer that the domain expert would have given. So what's our baseline here? Well, our baseline is just ask the model. This is very much how like we would interface with like ChatGPT or Claude today, where we just ask the model the answer. We're going to have turns of dialogue here where we can ask to critique or try to understand if the argument makes sense. And then our real goal is to work out and trust the expert because we're not certain if it's giving us the right or the incorrect answer. We'll use a 50-50 prior, which is the same uncertainty that you'd have over binary questions for this. Our method is going to be debate. This is adversarial. We're going to have two copies of the same model, and then we're going to have the non-expert judging them. The two copies are going to have turns of debate where they argue for their argument and produce critiques and rebuttals to the other model's arguments. And the hope is that these critiques or engagements with each other expose flaws in each other's arguments. Again, the debater's aim is to have their answer chosen. So it's set up to be like a zero-sum game between the two of them. We care about scalable oversight. So we care about how models are going to be when they're much smarter than humans. So we'd like some partial ordering over like debaters or model strength at the moment. So we're going to have lots of different debaters and try compare and see how our results change as models get smarter. We're going to have 23 different base model configurations, model configurations with 4 different base models, and we're going to optimize using best of n and critique. Finally, just to be able to measure things properly, we wanted to make this clear. The first thing we're going to do is like a protocol performance, which is how good the non-expert is when using these debaters or using consultants. And for the debates, we're going to use self-play here, which is 2 copies of the same model. But to compare models and like talk about their persuasiveness or their relative strengths compared to each other, we'll look at the win rate when we take 2 different models, we assign them roles in the debate, they argue, and then we switch those labels or those positions and run the debates again. We take the average over the 2 of them. Results. So the first thing to note here is that we're going to work out what our upper bound is, which is we're going to pretend, and we do this at the end actually, we give all of our judges access to the underlying text and see how good they could have done if they could have just read the text and answered the question. In particular here, you see that humans and GPT-4 Turbo get about 91%. And the reason this isn't 100% is because actually some of the quality questions are ambiguous. They're quite hard, and actually when you're reading them quickly or you're just trying to read them, you might actually miss out on the subtlety that like highlights the proper answer. The next thing to notice is like if we just don't give the model, the judges, the non-expert anything, we can ask them to guess. And 50% would be random chance here. And this is a good way to just measure data contamination. In particular, Claude 2.1 seems to have seen a couple of quality stories for whatever reason it's pre-training. This is really the lower bound of performance that you'd like. So what happens when we just ask the model? Well, it turns out if you just let language models talk to consultants or other language model experts, they're really gullible in comparison with humans who are quite good at like being like sus of bad argumentation. You see in general with LLMs, they actually get worse performance sometimes than naive because the dishonest consultant can sway them away. Humans are pretty good at sussing out bad arguments, so they have a really good score here. Debate massively improves accuracy. As you can see across the board with all judges, debate helps models really identify the truth. And in particular with humans, we get 87% here, which is only 4% short of if they had access to the underlying text. This is a really good result. We also looked at an augmentation of debate, which involves looking at allows the non-expert to direct the conversation at every turn of debate. This is incredibly interesting result because it shows for humans, when you have a good non-expert, this doesn't actually change the results. But for language models that are already pretty bad at highlighting bad arguments, being able to input and expose cruxes further is really, really useful. But why is this working? Well, let's compare debater performances and see what happens. Here is ELO rating versus models. Here you can see an ELO rating is a reparameterization of win rate. For context, the difference between GPT-4 Turbo and GPT 3.5 Turbo is around 400 ELO here, minus 300 to 100. That's like a win rate of 70%. So If you were to play these two models against each other, you'd expect 4 turbo to win 70% of the time, irrespective of what label it was given or argument or position it had to defend. Models under optimization become more persuasive, which is a great result. We'd expect models to get better as they trained in the game of debate. What's interesting here is they're training against judge signal, not ground truth labels, which means that actually you can do this kind of training even if you don't have ground truth labels in your new domain. And then the really interesting result is if you look at assignment as in position which a model is arguing for, you can see that models disproportionately get better when they're arguing for the correct answer versus the incorrect answer. This suggests that there is an advantage to this. In particular, this is probably equivalent to if you were watching games of chess and you notice the person who moves with white pieces is winning much more than the person who's moving with black pieces. In particular, what's interesting is as you get better overall at debating, you can exploit this advantage more. When we go back to self-play, to good old-fashioned protocol results, this should suggest that as models get smarter and they have to debate against a copy of themselves, being able to debate, arguing for the correct answer gives you a disproportionate advantage, which the judge can exploit. So judge accuracy goes up as models get smarter, which is a great result for scalable oversight. In summary, what have we shown you today? Debate is a suitable scalable oversight protocol in the quality hidden information setting. This is also a limitation in the fact that it's only the hidden information setting. Secondly, we show that debate between more persuasive models leads to higher judge accuracy, which we think is a great win. We have follow-up work, or the follow-up work exists already, but already is like trying to remove some of those limitations I've already said. And I just want to shout out both the Google DeepMind team, which is Zach Kenton and co, and the NYU team, which is Sam Armisen and co, who have been trying to either train language models directly via RL in debate or look at expanding debate to new domains. Thank you for your time. We will be at poster session. We will be at the poster session following this presentation in Hall C. Thank you for your time. Peace.